morning. We have been discussing distances for quite a few lectures. Today we are going to move over to a different topic. We are going to discuss the age of the universe. Right in the beginning, I have told you that if there is no gravity, if the universe expands freely, then the age is precisely 1 by h naught. And if we incorporate the effects of gravity, then the age of the universe depends also on the cosmological model. And we have derived an expression for the age of the universe. So, let me just go through it once more, it is very straightforward. dA dt 1 by A is the Hubble parameter, and we can usually write it as a function of the scale factor. So, from here it is quite obvious that T is equal to the integral dA divided by A into the Hubble parameter, and the limits of the integration should be 0 to 1 if you want the present age of the universe. So, the age that is predicted, h naught, h as a function of the scale factor depends on h naught and other cosmological parameters. So, the present age of the universe depends on the cosmological model. Now, whatever it be, the present age of the universe should be larger than the oldest object that we find in the universe. It would be, there would be some, I mean, it would be absurd if the universe was predicted to be younger than the oldest object that you found in the universe, because obviously all objects in the universe were created after the universe came into existence. Okay. So, the question is, how do we determine the age of objects in the universe? And we are interested in determining the age of really old objects, not objects whose ages are of the order of tens or hundreds or thousands of years. We are interested in determining the ages of objects where the ages are in the order of gigayears, 10 to the power 9 years, right. So, the question is, how does one determine such ages? Okay. Now, one technique which can be used for this is nuclear chronochemistry cosmology. Okay. So, it is called, basically it is nuclear chronology, and this is referred to as, in the context of cosmology, as nuclear chronocosmology. So, nuclear chronology can be used to determine the age of rocks. So, this is essentially related, closely related to earth science, geology. So, you can use these techniques to determine the age of rocks. How does this technique work? It is based on natural clocks, and the natural clocks are radioactive elements. So, there exist many heavy elements, not because there exist several heavy elements whose lifetimes are of the order of 10 gigayears. The age of the universe we have seen is of the order of 10 gigayears, right. So, there exist several heavy metals with lifetimes of the order of 10. So, these are unstable, radioactive, okay, heavy metals with lifetimes of the order of 10 gigayears. So, there are 3 nuclear reactions given over here. In the first reaction, you have thorium 232 going to lead, and the lifetime is 20.7 gigayears, lead with mass number 202. Then you have uranium 235 going over to again to lead with mass number 207. This has a lifetime of 1.02 gigayears. And uranium 238 goes over to lead with mass number 206, and this has a lifetime of 6.45 gigayears. Okay. Now, because of this radioactive decay, if at a certain time t equal to 0, wherever this need not be at the Big Bang, this is not at the Big Bang. At a certain time, there are N0 atoms of the parent nuclei, then the parent nuclei decays, and after a time t, the quantity that you are left with is Nt, which is N0 into exponential minus t by tau, where tau is the lifetime. Okay, it tells you the decay rate. So this is the usual formula describing the decay of radioactive particles. I am sure all of us are familiar with this. Okay, so you have this radioactive particle, you start off with some number, after some time the number falls, it has gone down by an exponential factor. Okay, so these can be used to determine the, so if you have such elements, then you can use these to determine the age of objects. So how are these used for age determination? Let me briefly discuss this. So for the purpose of age determination, it is useful if you have a nuclear reaction, a decay process, where a parent P, a parent nucleus P, decays to a single daughter nucleus. So this P decays to give you D. In the process, some radioactive particles, gamma ray, beta ray, etc., may be emitted. But as far as we are concerned, the P decays to D. Okay, that is what you have in the sample. And this is the only way in which D is produced. So whatever quantity of this element D that you find has been produced exclusively by this mechanism. There is no other way in which this isotope can be produced. Okay. Now, and all these three reactions have the same, satisfy these conditions. All the three reactions that I have shown here, nuclear reactions, satisfy these conditions. So once so suppose I have a sample, some material, once it is separated, isolated from the nuclear reaction, then once it is isolated from the nuclear reaction, then its abundances, we can write down its abundances as a function of by mass, how it evolves with time. Okay, let me do that. So once you have separated your sample, isolated it from the nuclear reaction, and these materials are all produced, the nuclear reaction occurs inside supernova. Okay, so once these material have been ejected from the supernova, so the nuclear reaction once it has stopped, then we can write down, after that we can write down this. So the daughter is produced by whatever, if there is some initial, so suppose we are looking at some time, we start at some time before which the reaction might have proceeded to some extent, then there will be some D0 amount abundance of the daughter already present, plus P0, that is the starting abundance of the parent, into 1 minus exponential minus T by tau. So this is the contribution from the decay, and this is what was there to start with at that instant when you, from where you are considering the evolution, and D is the abundance that you see at present. in your sample. Okay, so it will be related like this. You have a sample. This kind of a thing is typically done on rock samples. Okay, we want to estimate the age of the Earth, the age of the solar system. Okay, all the material in the solar system was produced in a supernova. I shall come to this topic shortly. Okay, but the thing is that we would like to estimate the age of the Earth or the age of the solar system. So, the age of the Earth can be estimated by finding the age of the oldest rock on the Earth's surface. Age of the solar system can be estimated if you find the age of meteorites. If they are older than the age of the rocks on the Earth, then you can say that they correspond, they give you an estimate of the lower limit to the age of the solar system. Solar system could be older than that, but it is a lower limit. Okay, so we would like to do this. So, for that you look at meteorites which come from our space within the solar system, they fall on the Earth's surface. Okay, so what you do is you determine these abundances in rock samples using mass spectroscopy. Okay, and if the whole thing started off at some time where this had an abundance D0, the parent had an abundance P0, then at the present instant it is going to be D, which are related like this. Now you can write this also as now P0 can also be written in terms of the present abundances. So we can write this as P exponential T by tau into this factor over here, which gives us the abundance of the daughter to be the initial abundance of the daughter plus P into exponential T by tau minus 1. Okay. So, we have a relation between the observed abundance of the daughter, the observed abundance of the parent, and the starting abundance of the daughter. So, if you knew the starting abundance, you could measure this and this, you could determine the age. Tau is known. People have measured tau, the decay rate, it is known. So, if you could measure this and this in the sample, you can then determine, and if you know this, what is the initial abundance, then you could determine the present age of the sample. Okay. The difficulty is that this is not known. Okay, this is not known. We don't know the abundance with which it started off when the sample was produced. That is not known. Okay, so that is the main difficulty. This is not known. Neither do you know the ratio of the initial abundance of the daughter to the initial abundance of the parent. Neither are any of these two known. Okay. Further, this ratio, the abundance of the daughter to the abundance of the parent, initially could be different in different parts of the sample. Same rock, it could be different because of chemical fractionation. Okay. Because these have different masses, so they could diffuse or various other processes, and the initial ratio itself could be different inside the sample or from sample to sample. Okay. So, this is the main difficulty, that we do not know this. This can be observed, this can be observed, tau is known, you can determine T provided you know this. So, the way this is overcome is as follows. What you have to do is, you have to look for an isotope which is stable, relatively stable isotope of the same daughter. Okay, so you have to look for a relatively stable isotope whose lifetime is much larger than this reaction. So you have to look for a relatively stable isotope of this daughter sample. Okay. So if you have a relatively stable isotope, then you can determine the abundance of that and divide okay. Now, if you assume that this ratio is constant initially across all the samples, if this ratio is constant, this will vary from parts of the sample to another part across samples. This will also vary, but if you assume that this is a constant, that the two isotopes had the same ratio at the beginning, then you make a plot of d by s versus rather other way around, you make a plot of p by s against d by s, whichever way you wish, p by s against d by s. This will be a straight line. The intercept of this straight line is going to give us this value, and the slope of the straight line is going to give us this value. And so you will have different data points, they will all be scattered, but they will all lie on this straight line. So this is unknown, they could be different, but they will all lie on this straight line, and from there you can determine this factor over here, and you get the age of the sample of the whole solar system from this. Okay. So that is the basic process by which these ages are determined, ages of rock samples are determined, and what are the results that you have from this analysis. So the results from this analysis are that the age of the solar system is 4.57 gigayears. Okay. Now please bear in mind that I am giving you certain figures which were the correct figures at a certain instant of time when I looked them up from some book. Now these things are liable to change, people continue to do research on this, so they might have found an older rock sample, etc. So these are representative figures, they may not be the currently accepted figures. Okay, they might have been improvements in this after that. Okay. So the age would not have gone down, it could have gone up after that. Okay. So age of the oldest rock on Earth is 3.7 gigayears, so the Earth obviously is a little younger than the whole solar system. Okay, so we have, from this analysis, we have an idea of the time scale of our solar system. How old is it, right? It's of the order of 4.5 billion years. Quite comparable, around half the age of the universe, a little less, maybe 1/3 of the age of the universe. Okay. This analysis also gives us the pre-solar abundances. So before it gives us the abundance. So yeah, sorry. This analysis also gives us the pre-solar abundances. It gives us this number, right, which has been assumed to be constant, and it is verified from the data that it is a constant. Okay. So this gives us the pre-solar abundance. It gives us the abundances of isotopes before the solar system was formed. Okay. And what these tell us is that the ratio of U-235 to uranium to 238 uranium is 0.33. The ratio of this isotope of thorium to this isotope of uranium 238 is 2.3. Okay, so when the solar system at the initial stage, the initial epoch of the solar system, when it was formed, before the solar system was formed, so this at the 0 point of this epoch, the rocks, these elements had these abundances. Okay. Now, question is then, can we find how long ago the pre-solar material was produced? Okay, so the previous analysis gives us the age since the formation of the solar system. Okay, and it also gives us the abundances of elements at the time when the solar system was formed, of these elements. Now, can we use this data to determine the time, the time that elapsed before these elements were formed and the solar system was formed? Okay. So, then you can do it if you know the abundances with which these elements are produced to start with, right. So, there will be, if you know the abundance with which these elements are produced, then you can find the time between the epoch when these elements were produced and when the solar system was formed, right, because then the abundances would have changed due to nuclear decay. So, this brings us to the topic of heavy metal production. How were these metals produced? How are these heavy elements produced? Okay. So, then one has to know something about this. Now, we shall learn as we go along this course that the universe started off, the early stages of the universe, the material, the constituents, the baryons were mainly in the form of hydrogen and helium. Okay, so what the elements that you can produce in the cosmological context are essentially hydrogen, helium, and few of the light elements. Okay. So, our universe by certain processes ends up with hydrogen, helium, and few of the light elements, lithium, etc., deuterium. Okay. But there is no way it can produce heavy elements. How are the heavy elements produced? Oxygen, all the things that we see here, carbon, oxygen, how are these produced? Now, these are produced by nuclear fusion inside stars. Okay, so inside stars there is nuclear fusion going on, very dense. See, for these reactions to take place, you need two things: you need high density and you need high energies. Nuclear fusion to take place. Right? Atoms have to, nuclei have to hit each other. For the nuclei to hit each other, the density should be large, otherwise they will not collide. And they have to overcome the Coulomb repulsion, because nuclei are positively charged. So, they have to overcome the Coulomb repulsion, come close together so that the nuclear attraction can take over. So, you need high energies for this. Okay, so such energies exist in the cores of stars. So, nuclear fusion takes place, you have a whole cycle, series of reactions, hydrogen goes to helium, helium then, okay, so you form carbon, etc., in this oxygen, all of these things inside this. Okay, but you cannot form elements beyond iron by this process. These are equilibrium processes. The binding energy per nucleon, it actually goes up all the way to iron. So, it's a stabler configuration. So, when two nuclei combine to form a bigger nuclei, the binding energy per nucleon goes down. Okay. So, it is more stable. So, the reaction proceeds in that direction. It is an equilibrium process. So, the reaction proceeds to, it has lower energy, so it goes in that direction. But this is true all the way up to only iron. Elements which have nuclei which are heavier than iron, the binding energy per nucleon again falls. So you cannot produce them by in equilibrium reactions. Okay, they are unstable relative to iron. So this was a big problem, figuring out how these reactions, how these elements are produced, and it was finally figured out that these elements are produced in supernova. So supernova inside, so nuclear fusion can produce all the way up to iron, and after that very massive stars, they explode. Okay, at the end of their life they explode. At this epoch, when they explode, there are very high neutron fluxes. So there is a high neutron flux at that epoch. Now these nuclei, when they experience this neutron flux, they capture neutron. Okay, so these elements beyond iron are produced by neutron capture in supernova. Okay, lead, all of these elements, all these heavy metals that we have on Earth, they were all produced in some supernova or the other. Okay, in the past. So they are produced by neutron capture, and neutron capture, there are two processes. There is the R process. In the R process, the neutron capture rate is faster than the rate at which the nucleus decays. Okay, there are two competing processes. The nuclei capture neutron and they also decay. So here this is R process where the capture is, neutron capture is faster. There is also the slow process, S process, where the neutron capture is slower than the decay. So these metals, these elements that we are discussing, were produced by the R process. Okay. So people have an idea now of how these elements were produced. They were produced in supernova. So what we would like to know is the abundances at the end of the supernova that produced these elements. And we know the abundances when the solar system was formed, pre-solar system. So you can find the time that elapses between these two events. Okay. And this will give us an estimate of the age of the galaxy. The supernova which exploded were there in our galaxy. The material gets recycled within our galaxy. Okay, so this will give us an estimate of the lower limit to the age of our galaxy. It could be more. The supernova obviously did not occur, possibly did not occur right at the birth of the galaxy. So there could be some time there also. Okay. Now this was first, so these reactions and things were first worked out in famous papers by Burbage, Hoyle and Fowler. Okay, these four people in 1957. And Fowler received the Nobel Prize for his contribution to how the elements were synthesized, these heavy metals. Now an updated calculation of the same thing in 1988 by Fowler. So he did some calculation, revised the nuclear rates, etc., and in 1988, so this is based on that, and so these calculations predict that the uranium abundances have this ratio at the end of the supernova, and the thorium to uranium ratio is 1.7. Okay, so these give two different ages, two different times which elapsed between the supernova and the formation of the solar system. So these ages are 1.6 and 2.9 gigayears. Okay, so this you also required to put in other inputs. The material was not formed by just one supernova. There could have been a whole sequence of supernovas before that. Okay, so that has to do with the star formation history. The supernovas occur very close to star formation. It is the massive stars which give rise to supernova. The massive stars don't live long. Okay, so it has to do with the star formation history. So there are inputs from that also. So finally, we are interested in the numbers. So, without going into the details, these are the numbers. So, now if you adopt this larger number 2.9 gigayears, then it tells us that the age of the galaxy, of our galaxy, is more than 7.5 gigayears. Okay, this gives a lower limit to the age of the galaxy from this nuclear chronology. Okay. So, now let us move over to a different method for age estimation. This was one method of age estimation. So, it tells us that our galaxy is 7.5 gigayears old, at least 7.5 gigayears old. So, whatever model, whatever age your model, cosmological model predicts, should be at least more than 7.5 gigayears. Okay, it could be much more than that, no harm, but if it is smaller than that, then you are in difficulty. Another method which is used for determining ages is based on globular clusters. I have already introduced globular clusters right in the beginning, possibly the first or second lecture. So, these are collection of stars, and there are many such globular clusters in the halo of our galaxy. You can also see them in other around other galaxies. There are 10 to the power 5 to 10 to the power 6 stars in the globular cluster. They look like this. It is a collection of stars that look like this, and they are old stars typically, okay, all old stars. Now, the age determination of globular cluster is based on the assumption that all the stars in the globular cluster were formed together, which is quite a reasonable assumption. Okay, so, all the stars that you see in a globular cluster were formed together. So, they were formed at some time in the past simultaneously, roughly simultaneously, and we would like to determine the age that has elapsed since that instant. Okay. Now, to understand this age determination process using globular clusters, we have to take a look again at the HR diagram. Again, the HR diagram was also introduced as a means of determining distances. So, let me just briefly recollect what the HR diagram is and then go ahead. So, the HR diagram, the theoretical HR diagram, has along the x axis the temperature, right. So, this side is hotter, this side is cooler. This is the temperature of the star, and along the y axis is the luminosity, the total light emitted by the star. So, it is found that the majority of the stars reside along a track like this, which is called the main sequence. And on the main sequence you have the red stars which are smaller, and you have the blue stars which are brighter, like this, which are fainter. Here the red stars are fainter, the blue stars are brighter, and there is a whole graduation in between. This is called the main sequence. Now, the main sequence on which the majority of the stars lie is the hydrogen burning phase of the star. So, a star is a gas, is basically a sphere made up of gas, spherical gas distribution, and the interior is much hotter than the exterior. Exterior of the sun, the radiation that we get from the sun is roughly 6000 Kelvin, right. So, we can just look at this graph. This gives you the range of temperatures that you have. It gets hotter and hotter. So, it starts from around 2000 and goes all the way to 40 tens of thousand Kelvin. Okay. The interior is much hotter, and there is nuclear fusion going on. So, hydrogen, that is what provides the fuel, otherwise the whole thing would have collapsed. So, there is hydrogen burning, hydrogen, they fuse together, give you helium. Okay. So, that is the reaction that takes place at the core center. Now, this properties of the star that is burning hydrogen is well understood. Okay. And these properties do not really depend very crucially on the source of the nuclear reaction. As long as there is some nuclear reaction, hydrogen burning, so these properties are quite general. They depend, so you can derive these properties, not very difficult. These properties depend on two things. One of them is the virial theorem. The virial theorem, I will urge you to look it up, is a relation between the kinetic energy and the potential energy of an object in equilibrium. So if there is an object in equilibrium, so the object is neither collapsing nor expanding, then you can predict a relation between the kinetic energy and the potential energy. Okay. They are related, they cannot be independent, arbitrary. And that relation depends on the potential. So you have the gravitational potential for which you can predict what the relation is. The second thing is that to support this, the star, so inside the star the radiation contributes to the pressure also. The radiation is coming out, and in the process of coming out, the light that is produced in the center of the star does not just travel straight out. It gets scattered, and it takes a considerable amount of time. I think it's around millions of years for the photon produced at the center to finally come out. It gets scattered and it does a random walk inside. Okay. So you have to assume, which is the right assumption, that it is Thomson scattering that mainly contributes to this opacity. So you cannot, what we mean by opacity is that you really do not see the interior of the star, what you see is the surface. It is opaque, and this opacity is due to Thomson scattering. Thomson scattering is the scattering of a photon from a charged particle, charged electron. You must have studied about it. The frequency does not change in the process. Okay, it is an elastic scattering. So with these assumptions, you can derive the properties that you expect for stars if they are burning hydrogen in equilibrium. So it is a gas, essentially a gas in equilibrium. Okay. And the properties that you arrive at with these assumptions, they are that the luminosity is proportional to the cube of the mass. The more massive the object, the star, the gas, the sphere of gas, the more luminous it is, and it goes up as the cube of the mass. So if you double the mass, the luminosity will increase 8 times. Okay. The temperature of the star, okay, these three are not independent. The luminosity you can work out if you know the temperature and the radius. Luminosity is 4 pi r square sigma t to the power 4. So you can work out, and you will find this mass to the power of 3. Okay, so the temperature is proportional to the mass to the power of 0.5, and the radius is proportional to the mass to the power of 0.5 also. Okay, so both of these are proportional to the square root of the mass, the temperature and the radius. And with these things you can also understand the HR diagram, because you have the luminosity here, you have the temperature here. Okay, this is a logarithmic scale, so you expect a straight line here, and you can determine the slope of this. This will give you some rough idea. Now, the lifetime of a star, let us say it is tau. A star lives on the main sequence as long it has hydrogen to burn. So the lifetime into the luminosity, so the rate at which it is burning, sending out energy into the lifetime, this is the total energy that is sent out. This will be comparable to the mass of the star into c square. It sends out a fraction of its mass. The fusion essentially converts mass into energy, right? And the mass is in the hydrogen. So when it exhausts the mass, the hydrogen, when the hydrogen is finished, the life gets over. So the lifetime into the luminosity, the total energy that is emitted, is essentially proportional to mc square. Okay, that is the energy available. And mass we have seen can be written, so this is proportional, okay. The mass we have seen can be written as in terms of the luminosity as L to the power of 1/3. So forget about c square, or the lifetime of a star is proportional to L to the power minus 2/3. So briefly, the more massive stars are more luminous, so they lose energy faster, so they finish off their fuel faster. The less luminous stars, they burn slowly, so they live longer. Okay. So the lifetime is related to the luminosity as L to the power minus 2/3. So what you see from this analysis, this brief analysis, is from this is that the bigger stars have shorter lives. Okay, so the more luminous stars, the more massive stars, they have shorter lives. Why? Because they burn off their fuel, and one can work out these things from just these basic ideas. So if you look at the HR diagram of a globular cluster, so this is the HR diagram in general for a, say, an open cluster. This we had discussed this in the context of an open cluster. Open cluster is one which has been formed quite recently, so you have all kinds of stars. Now a globular cluster is an old object, so what happens is that beyond a certain luminosity, depending on the age, beyond a certain luminosity, the stars have burnt their fuel, finished, hydrogen fuel is over. So the whole HR diagram actually extends all the way here, or this is the same thing. I have just shown you two pictures of the same thing. Whole HR diagram extends all the way like this, but depending on the age, the stars in this part have all exhausted their fuel. So they no longer, what happens when the star exhausts its fuel? Okay. So when a star exhausts its fuel, brief, I am just telling you in brief. Okay. So a star has exhausted all its fuel. So it initially goes into the subgiant branch. The temperature falls a little and the luminosity remains a constant. So this stars beyond this have finished their fuel. You can see from here, these stars lie on the main sequence. The stars which are beyond this, so this was the whole main sequence to start with. Okay. Now stars over here have finished their fuel, and once a star finishes its fuel, the hydrogen fuel in the center has gone. Okay, there is helium in the center. Now this star, initially what it does, once it finishes its fuel, its temperature will go down. So it will, okay, before that, before I go into that discussion, there is another point which I should have made. You see, this is an observational HR diagram, not a theoretical one. This is an observational HR diagram. Now here what is plotted is slightly different. The thing plotted along the x-axis is the B minus V color. I have discussed what B and V are. They are the magnitude in the B band and the magnitude in the V band, blue and visible. Okay, so the difference of these two magnitudes is the ratio of the observed fluxes. Okay, and they give you an estimate of the color. Okay, so the red stars will have more in the V, more light in the V band than in the blue band. The blue stars will have more light in the blue band than in the visible band. So this difference gives you the color. Okay, it's a ratio of the fluxes, it gives you the color. And the apparent magnitude, which can also be converted to the absolute magnitude if you know the distance, that gives you the luminosity. So that is what is plotted over here. Okay, this is the observational HR diagram. both have the same both are the same observational HR diagram. Okay, they are different. They possibly correspond to different clusters, but they are the same quantities are plotted. So once the star exhausts its hydrogen in the center, it becomes a subgiant. Its temperature falls, so it moves horizontally this way. Its luminosity remains constant, roughly constant. Okay, so it is over here in this part. And then then it reaches a phase where its temperature is a constant, its luminosity increases. Okay. So what happens over here in this stage, in the subgiant stage, is that in the core there is helium burning. So once the hydrogen is burnt in the center, the core collapses. Okay, it collapses, it no longer is that big. The center of the star where the hydrogen has been burnt collapses, and that is now supported by degeneracy pressure, and then helium burning starts over there. Hydrogen burning, there is an outer envelope that expands 10 times. Okay, and hydrogen burning occurs over there in the outer shell. Still, hydrogen has not finished outside, it has finished in the center. So when the core collapses and the outer part expands, initially the luminosity, the outer part is not yet expanded, the temperature falls, and then the star moves like a subgiant, and then the outer part expands 10 times. The nuclear reaction rate also goes up, hydrogen burning in the shell goes up. So the temperature here remains roughly a constant. This is the red giant branch phase. Okay, red giant branch. So there is a subgiant and then there is a red giant. The outer shell expands 10 times. That is why it becomes a giant. Okay, the luminosity goes up. The temperature remains more or less constant as the H1 burning in the shell goes up. Okay, this is a red giant phase here. Okay, so all of this is after the hydrogen in the core has been exhausted. And then there are other stages which I shall not discuss. This is the asymptotic giant branch. Okay, this is the horizontal branch where the star becomes very hot. Okay, so this side the temperature increases, up the luminosity increases. Okay, so the crucial point is that once a star exhausts its hydrogen fuel in the center, it leaves the main sequence and proceeds on this track. You will not see a star moving on this track. What you will see is that the star has left the main sequence, it is somewhere here, somewhere here, somewhere here. Stars which have left earlier will be here or even further. Stars which have just left will be somewhere here. Okay, this occurs on a much larger time scale, millions of years. Okay. So the longer you wait, so right in the beginning, the more luminous stars will finish their fuel and they will leave the main sequence. As it gets older and older, less luminous stars will leave the main sequence. Okay, so as the evolution proceeds, this turn off point is going to move further like this, right, because we have seen that the age is proportional to L to the power minus 2/3. So as time increases, the turn off point is going to move to lower and lower luminosities. Lower and lower luminosities, they are going to exhaust their fuel. Okay. Now, so the turn off point, the point where there is a turn off from the main sequence, that gives an estimate of the age of the globular cluster. Essentially, it tells you straight away. Right, older globular cluster, the turn off point is going to be below. It is going to be at a smaller luminosity. Newer globular cluster is going to be further up. A young cluster, open cluster, you are going to see the whole HR diagram, no turn off. Okay. So People who work on stellar theory, they have worked out evolutionary tracks, how the star moves on the HR diagram. So there it will move into the subgiant, then there will be a red giant, okay, then there is an asymptotic giant branch, and then it will go into the horizontal branch. So all of this has been worked out in detail, and what they do is they calculate what are called isochrones. Isochrones, okay. So what is an isochrone? Suppose I assume that my globular cluster has a certain age, then I will get a curve on which the stars should lie. For a different age, I will get a different curve. Okay. So let me just draw a schematic picture. For a particular age on this HR diagram, I will get a curve that roughly looks like this. Okay. For a smaller age, I will get a curve, maybe, okay, some curve. For a larger age, the turnoff will occur somewhere over here, and maybe all of this will be the same. Okay. So these are called isochrones. So for a particular age, there will be one such curve. And what they do is then you fit these isochrones and find out for which age you get a good fit to the data of a particular globular cluster. Okay. There are certain problems with this, like any other observational idea, there are problems. So the first problem is that the distance is unknown. So you have the freedom of moving the curve up and down, right, because what you have is the absolute, not the absolute magnitude, but the apparent magnitude. You can add a distance, it will move the curve up and down. Also there is metallicity. So the whole evolutionary track depends on the metallicity of the globular cluster. So it depends on the chemical composition of the material from which the globular cluster itself was produced. Okay. So if you have a little more metal, maybe the evolution is slightly different. And further, there is reddening inside the globular cluster, and as the light propagates to us, it gets absorbed by dust. Okay. So that can also change the magnitudes and introduce complications. The results from this analysis, the ages turn out to be in the range 13 to 17 gigayears. Now people believe that 17 gigayears is possibly too high, it's erroneous. Okay, it's an overestimate, some error has crept in. Reliable estimate, okay, representative value is 15 gigayears plus minus 1.5. 15 plus minus 1.5 gigayears. This is a representative value. So each globular cluster will give you a different value. They are in this range. This is a representative value. People are quite confident, 95% confidence, that the age of the globular clusters are more than 12 gigayears. Okay, so the whole age of the universe had better be more than 12 gigayears. Okay, now let us come to the parameters, cosmological models. So I have told you we have discussed two methods by which to determine the age of the universe. There are other methods also. Now let us come to the cosmological model. So I have explained right in the beginning that the age of the universe predicted by a cosmological model will depend on the parameters in the model. Okay, the choice of parameters. And we are working with we have been discussing a cosmological model where there is omega matter, omega lambda, and omega curvature. And the total sum has to be 1, so 2 of them are sufficient. We have had a look at this kind of a diagram in the last class, so I am not going to explain what these various things are. Now, these are the constraints you get from supernova data. Supernova data tells us that with 68% confidence, the value corresponding to our universe should lie in this interval, 95% confidence it should lie in this interval, etc. Now, for a given choice of these two parameters and a choice of the Hubble parameter, so these you can determine the age of the universe. So if you fix the age, you get contours on this. So there are combinations of omega matter, omega lambda, which produce the same age. It is not unique. Okay. So, this shows you the age. Suppose I had chosen a large matter content, no cosmological constant, then the age is going to be small. Okay. That is something I have explained. If the universe does not expand, so what we have from observations is the slope over here at a certain time. If the universe does not expand, this, if the universe, the age gets reduced. If the deacceleration is more, the age gets reduced. Okay, if the universe is accelerating, then the age gets increased. So, putting in a cosmological constant for the same omega matter will give you a larger age of the universe. Okay. So, these are the contours of along which the age is a constant. So, this is the contour of 16 gigayears. Okay. This is the contour of 16 gigayears, this is the contour of 14 gigayears. So, if you take 15 as the value, then it will be somewhere over here in between, okay, which is quite consistent with the parameters indicated by the supernova and W map. We had seen the favored parameter in the last class, omega matter 0.3 and omega lambda 0.7 somewhere over here. Okay. Certain parts of the allowed parameter space are just ruled out by the age that is predicted is too small. Okay. So, the age of the universe, as I have shown today, puts very useful constraints on allowed cosmological models, and models which predict an age that is too small are obviously ruled out. I have also told you how you can determine the age, the lower limits for the age of the universe, and the universe has to be obviously older than the oldest object that you see. So, let me stop here and we will move on to a different topic in the next class.